Good morning, everyone. In this video, we will continue discussing the topic that we have started in the previous video, which is the alkyl halides. As we have mentioned, these are aliphatic compounds having a halogen atom attached to the carbon. The halogen is highly electronegative, so it attracts the electrons of the bond, producing a partial negative charge on the halogen and a partial positive charge on the carbon. As we have mentioned, you have three major types of reactions: the formation of the Grignard, and this one involves the reaction with a magnesium metal to be placed between the carbon and the halogen, and accordingly the carbon will carry a partial negative charge. The second reaction is the nucleophilic substitution reaction, and we have divided them into SN1 and SN2 reactions. Finally, we have the elimination reaction, where we eliminate a hydrogen halide molecule from the alkyl halide, giving an alkene. This reaction, we have dealt with it in the preparation of alkenes and in the preparation of alkynes, where we place a halogen on one carbon and a hydrogen on the other carbon, resulting into the elimination of the hydrogen halide in presence of a base. And if you remember, the base was usually alcoholic potassium hydroxide or sodamide, where you eliminated an acid molecule, which is the hydrogen halide. Let's discuss this elimination reaction in full details. As in case of the substitution reaction, we had an SN1 and an SN2 mechanism. Again, in the elimination reaction, we will have an E1 and an E2 mechanism. As you have guessed, the E2 will involve a bimolecular mechanism, and the E1 will involve a unimolecular mechanism. In case of the E2, you will have the base and the alkyl halide present in the first step. However, in case of the E1, you will have the alkyl halide by itself first, and then the second step will involve the base. Let's look at both mechanisms. First, let's discuss the bimolecular, because it's the normal or the most popular, or the mechanism that actually takes place during an elimination reaction. In this mechanism, you have the carbons, two carbons attached to each other. One of them is carrying a halogen and the other one is carrying a hydrogen, and you attack by a base. The base will abstract the proton. The proton will leave its electrons for the carbon to produce a double bond with the other carbon, and the halogen will leave, giving the double bond. Before the double bond is formed, you have a stage where all bonds are still partially formed, partially broken. Not broken bond, the broken bonds are not yet broken, and the formed bonds are not yet formed. And then the reaction proceeds to give the doubly bonded compound. As you can see, the first, or the slow step, involves both the base and the alkyl halide, so it's called a bimolecular elimination reaction. In case of the unimolecular, you will have the halogen leaving first, exactly as we said in case of the unimolecular substitution reaction. The halogen will leave first, and then the base will abstract the proton to give the double bond of the compound. As you can see, the first slow step involves only the alkyl halide, so it's an E1 mechanism, while in the first one you had both molecules, the base and the alkyl halide, in the first step, so it was a bimolecular reaction. Just as a small hint, you should know that a unimolecular elimination reaction is a rare reaction. It takes place in very, very rare conditions that we will not deal with in this course. Okay, they are very rare, and they will be dealt with in more advanced postgraduate courses. So whenever you perform an elimination reaction, you should always think of the E2 rather than the E1 mechanism. Why are we studying the E1 mechanism? We are studying the E1 mechanism because it's the reason for some minor products that we get when we are performing our regular reactions. Okay? But however, in the exam, when you are asked to decide on the mechanism, never think of the E1 in this course. We have not discussed the cases when E1 takes place. So just think of the SN1, the SN2, and the E2 mechanism. Now, if we discuss the factors that will decide on which mechanism will take place, whether elimination or substitution, we will deal with the two main factors. The first factor is the nature of the alkyl halide, and the second factor is the nature of the base. Exactly the same as we have done in case of the substitution reaction. We dealt with the nature of the alkyl halide and the nature of the base. Whenever you have a tertiary alkyl halide, it prefers to go through elimination than the secondary, than the primary, than the methyl. The methyl cannot perform elimination whatsoever because it does not have two carbons. It actually has one carbon. So this is the ease of the reaction. Two reactions prefer the tertiary, then the secondary, then the primary. And the tertiary usually prefers the elimination rather than the substitution reaction. As for the nature of the base, the stronger the base, the ease of the elimination reaction. Okay, so how do we choose? Let's think of it. In the substitution reaction, we said that a strong nucleophile will prefer SN2 over SN1. Okay, and we have the cyanide followed by the iodide, followed by the alkoxides and the hydroxides. If we try to arrange the bases according to their strength, you will notice that now the strong base, arrangement of bases according to their strength, you will notice that the alkoxides are the strongest, followed by the hydroxides, followed by the cyanide groups. Let's first try to find what is the difference. I'll try to determine what is the difference between a nucleophile and a base. Usually a nucleophile is a base and a base is a nucleophile. So what is the difference between them? A nucleophile is something looking for a positive charge. It is carrying a negative charge, so it's looking for something that is carrying a positive charge. While a base is something that is looking for a proton. A proton is an atom carrying a positive charge, but not any atom, the hydrogen atom. It's a hydrogen atom carrying a positive charge. So this is the minor difference between what is known as a base and what is known as a nucleophile. A base is looking for not anything that is carrying positive. No, it's looking for a proton. It's looking for a hydrogen that is carrying a positive, not just any molecule, not just any atom or molecule carrying a positive. It prefers a proton. It's looking for a proton. This is a base. While a nucleophile, it does not differentiate whether it's a proton or any other thing that is carrying a positive charge. It's all the same. As long as it is carrying a positive charge, it's okay. So this is the slight difference between a base and a nucleophile. So a nucleophile looks for anything that is carrying positive. A base looks for a proton. Suppose that we are using a base. So the base is looking for a proton. If it does not find a proton, a base is looking for a proton. It wants a proton, not just anything that is carrying positive. It wants a proton. Suppose it did not find a proton. There was no acidic proton in the molecule for the base to attack. It will have to react as a nucleophile. it cannot act as a base now. A base is looking for a proton, and a proton does not exist. So it will have to go for anything that is carrying a positive charge. So a base, a strong base, is looking for a proton, while a strong nucleophile is looking for anything that is carrying a positive charge, no matter what it is. So to summarize this, let's look at what are the different possibilities that will face us whenever we are reacting with an alkyl halide. If you have an alkyl halide and you reacted with a hydroxide, for example, sodium hydroxide or potassium hydroxide, in the form of alcoholic medium, they have to be alcoholic sodium hydroxide or potassium hydroxide, or if you react them with alkoxides, you will always think of the elimination reaction, no matter what the type of alkyl halide is, and it will be an E2 mechanism. However, if you are using a cyanide, a thiol, or any other moiety that is carrying a negative charge, but it's not a base, it's not an alkoxide, nor it is an alcoholic potassium hydroxide or a sodium hydroxide, you will think of the SN2 mechanism and you will perform a substitution reaction. So, as we have mentioned, we have the third type of reactions, which is the elimination reactions. This involves dehydrohalogenation of an alkyl halide, where a hydrogen and a halogen leaves in presence of a base, an example of which is alcoholic potassium hydroxide, and you end up with the doubly bonded compound. You can proceed through an E1 or an E2 mechanism. As we have mentioned, the E2 mechanism involves the attack of the strong base right from the beginning, attacking the hydrogen, producing a double bond between the two carbons, and then the halogen leaves. You have a transition state which is very unstable, where no bonds are still formed and no bonds are still broken, just partial bonds formation and partial bonds breakage. And then you have a fast step where the double bond is formed. As for the unimolecular elimination reaction, you will have the halogen leaving first, putting a positive charge on the carbon, and then the base will attack the hydrogen, removing the proton and producing a double bond in the compound, in the final product. As we have mentioned, the factors affecting which type of reaction will take place are the nature of the substrate, which is the nature of the alkyl halide, and the nature of the base used. The tertiary, as we already know, as we have already discussed, the tertiary will prefer the elimination, then the secondary, then the primary, and then the base, the more the strength of the base, it will prefer the E2 mechanism. You do not really care about the fact that weak bases prefer E1 mechanism, since, as I have mentioned, you do not need to guess which reaction will go through an E1 mechanism, because we did not discuss these cases. To clarify when to use which mechanism, we will look at the different options that can face us, or we can come across when we are trying to perform a reaction. First, we will start with the simplest, which is the methyl halides. A methyl halide is not a primary, nor a secondary, nor a tertiary halide, alkyl halide, because the methyl has a carbon which is not attached to any carbons. So it's not primary, nor secondary, nor tertiary. If you are dealing with a methyl halide, you have only one option, which is the SN2 mechanism. It will never proceed through an SN1 because the methyl carbocation is not stable, so it will not be formed. So SN1 mechanism is not an option. And it does not have a second carbon to form a double bond with. so it will not perform an E2 mechanism. So you only have one option, which is the SN2 mechanism. When we move to the primary alkyl halides, we will have two options. As we have said, primary alkyl halides prefer the bimolecular mechanism. So you have two options. It's either the SN2 mechanism or the E2 mechanism. It proceeds through the SN2 mechanism when it reacts with a strong nucleophile. And it proceeds through an E2 mechanism if it reacts with a strong base. Examples of a strong base are the alk oxides and the alcoholic potassium hydroxide or alcoholic sodium hydroxide. This is when you think of an E2 mechanism. When you think of an SN2 mechanism, in case of the primary alkyl halides, you will have things like cyanide, thiols. You can have a hydroxide, you can have sodium hydroxide, but it will not be an alcoholic. It will be an aqueous sodium hydroxide or an aqueous potassium hydroxide. In this case, you have weakened your nucleophile, you have weakened your reagent. It's no longer a strong base, it's a strong nucleophile, so it proceeds through an SN2 mechanism. If you have a tertiary, let's skip the secondary for a moment and go to the tertiary. The tertiary alkyl halides will prefer again the unimolecular mechanism. So it will react using an SN1 mechanism. So if you have a tertiary alkyl halide and you reacted with a nucleophile, usually it's a weak nucleophile, you will end up having an SN1 mechanism. Suppose you used a strong base on your alkyl halide. It's a tertiary alkyl halide. It will proceed through the E2. Do not be mistaken. You cannot use the E1 mechanism. It will proceed through the E2 mechanism, the elimination reaction. Okay, let's go now to the secondary alkyl halides. If you have a secondary alkyl halide, it can actually go through all three mechanisms. So you have the secondary alkyl halide. It can perform the SN1, it can perform the SN2, and it can perform the E2. When will it perform each one? If you have a weak nucleophile, you will go through the SN1 mechanism, examples of which are the water and the alcohol. You will proceed through the SN1 mechanism. If you have a strong nucleophile, examples of which are the cyanide group, the thiol group, the aqueous sodium hydroxide, and the aqueous potassium hydroxide groups, all these will proceed through the SN2 mechanism. If you have a strong base, examples of which are the alk oxides or the alcoholic potassium hydroxide or alcoholic sodium hydroxide, you will proceed through the elimination mechanism. So again, the method only gives SN2. The primary will give the SN2 and the E2, depending on whether it's a strong base or a strong nucleophile. Strong nucleophile will give the substitution, strong base will give the elimination. The tertiary proceeds through both elimination or substitution. In case of substitution, it will definitely prefer the SN1, the unimolecular mechanism, because it has a huge static hindrance. So it will proceed through the SN1 mechanism. However, if it's forced through using a strong base to perform elimination, it will have to perform an E2 elimination because the E1 is a very rare reaction. The secondary is the one that can actually perform the three types of reactions, and that's why it's confusing, and that's why I have left it to the end. It can perform both types of substitution, and it can perform the only available type of elimination. Accordingly, it will depend on the nature of the reagent used. If it's a nucleophile, I will have to decide on whether it's a strong or weak nucleophile. A weak nucleophile will give the SN1. A strong nucleophile will give the SN2. If it's a strong base, and we have specific examples for strong bases, these are the alkoxides and the alcoholic sodium or potassium hydroxides. These will give the elimination reactions. Now, if we look at the organized slides, as I have just mentioned, the methyl halides will give the nucleophilic substitution reaction. It will not give an elimination reaction, no matter what we use, and the type of substitution will be the SN2 substitution reactions. If we use a primary alkyl halide, it will depend on the nature of the reagent. If it's a nucleophile, we will go through the SN2 as a major product. If it's a base, we will go to the E2 as a major product. We usually when I ask in the exam for the product, I'm asking for the major product. I do not care if you remember the minor product or not. You do not have to put the minor product in the in your answer. You do not have to include the minor product in your answer. I only care about the major product. This is why we are performing the reaction, to get the major product. We're not doing it to get the minor product, okay? We're just discussing the minor product to know what kind of impurities to expect in the product. That's it. Now, if we have a secondary alkyl halide, as we said, it can proceed through the three mechanisms, whether SN1, SN2, or E2. The SN2 will be performed if we are using a strong nucleophile. The SN1 will take place if we are using a weak nucleophile, and the E2 will take place if we are using a strong base. In case of tertiary alkyl halides, as we said, it can perform the substitution and the elimination. However, in case of the substitution, it only uses the unimolecular mechanism in presence of a weak nucleophile, giving a major product of the substitution as SN1 mechanism. If we use a strong base, it will proceed through the E2 mechanism. Since the E1 is a rare mechanism, it does not take place except in very rare cases, and it will give the doubly bonded compound. To summarize, we have the alkyl halides. They can be synthesized through 4 different methods: halogenation of alkanes by free radical mechanism, addition on alkenes or alkynes by Markovnikov or anti-Markovnikov, and finally replacement of an OH of an alcohol by a halogen using 3 different conditions: either halogen halide in presence of zinc chloride, or phosphorus reagents, or thionyl. And as we have mentioned, the thionyl halides are the best reagent if my starting material is not acid sensitive, because the byproducts of such a reaction are gases. The reactions of these compounds are 3 main reactions: either the formation of Grignard using magnesium in dry solvent, or substitution reactions. These are the SN1 or the SN2. The SN1 are done by the tertiary alkyl halides, and the secondary. They are not performed by the primary nor the methods. In both cases, we have to use a weak nucleophile. In case of the SN2 reactions, they take place in case of the primary, the methyl, and the secondary, and we have to use a strong nucleophile in this case. In case of elimination reaction, which is the 3rd type of reactions, we use a base, and we reacted with an alkyl halide. If the alkyl halide is a primary or secondary or tertiary, in all cases the elimination will be an E2 and it will not be an E1. E1 is a rare reaction mechanism that takes place in very minor cases. This way we have finished discussing the alkyl halides. I hope you have benefited from the videos, both parts, part 1 and part 2. And in the next video we will be discussing the aromaticity phenomena of organic compounds.